Shepard, you need to share those blueberries with your brother.
I want some cool fish.
Absolutely not.
Can I what's these blueberries?
You can share with your brother. Shepard, share with your brother.
5 minutes later.
Shepard, I thought I told you to share with him.
I did. He just ate his blueberries fast.
Well, you're still eating. Can he have 2 more? Give him 2 more. Eat the 2 blueberries that Shepard just put on the counter for you. I am never gonna get this video done. Good morning, good afternoon, good evening, and good night. All time blends together these days, but here we are. We are going to look at a lesson 11-4, dividing rational expressions. As always, we're gonna skip the get ready. I'm on page 587, and let's jump right into it. So we are dividing rational expressions here. We are going to spend 2 different lessons on dividing rational expressions. One of them, this first one, you'll see quite quickly, is very closely based on what we've already done in 11-3, multiplying rational expressions. Essentially, with one slight tweak at the beginning of the process, either we're going to notice common factors in our numerators and our denominators, and we are going to cancel those out, or we're not, and we're really not going to worry about it so much. We're just going to leave expressions as they are. In the next lesson, when we get to 11-5, which is dividing by polynomials, or dividing polynomials, we're going to do something that looks more like the actual process of division, as opposed to simply canceling things out. But we'll worry about that when we get there. Let's jump right into example 1. So again, I am on page 587 in your Glencoe Algebra 1 textbook, and I'm looking at example 1a, which has these expressions: 5x squared divided by 7, rational expression, looks like a fraction, divided by 10x cubed on 21. So here's the slight adjustment we're going to make at the beginning of this process. This certainly looks like fraction divided by fraction. And again, what hopefully is the consistent message you're hearing over and over again in chapter 11 is that if 2 objects, or if some object looks like a fraction, we can probably for the most part treat it like a fraction, with some small exceptions, which I'll get to in just a second. Imagine that this were simply 5/7 divided by 10/21. That is, that there wasn't actually any variable in this expression at all. Hopefully you would say, oh, dividing by a fraction, we're really supposed to multiply by reciprocals, right? Or what you all often call keep, switch, flip. We keep the 5/7 5/7, we switch the division to multiplication, and then we flip. The 10 goes from the numerator to the denominator, the 21 goes from the denominator to the numerator. Now it's worth pausing because, unsurprisingly, I don't like these random phrases that you sometimes memorize and don't really understand. It's worth pausing. Why do we do this? Why do we divide by reciprocals? If I said to do something like find half of 10, probably you do not do this process in your mind. 10 times 1/2, and then you put the over 1 part, you multiply across the top. 10 times 1 is 10, 1 times 2 is 2, and then you cancel and you get 5/1, which of course we write as 5. Again, it's overwhelmingly likely that's not what you did in your head right now. Although, based on what I said, remember of is typically multiplication, and of course I mentioned half. This is technically the right way to set it up. But no, when I said find half of 10, what you almost certainly did is you just thought to yourself, well, what's 10 divided by 2? And of course, that answer is 5. Same answer, right? So you have an intuitive connection in your mind between finding half of something, half times something, and dividing by the reciprocal of 1/2, which is 2. The same thing goes for any whole number. If I say find 1/3 of something, find 1/3 of 24, probably in your head you don't multiply 24/1 times 1/3. You probably literally think, well, how many times does 3 go into 24? Or even if I said something like, how many times does 2.5 go into 10? Hopefully you thought to yourself right away, oh, that's 4, right? 2.5 goes into 10 4 times. But literally what we're doing there is we're saying, well, what if we wanted to divide 10 by 2.5, which is another way of saying divide 10 by 5 over 2, because that's the fraction. And then from there, we could say, oh, well, that's the same thing as 10 times 2 over 5, right? 10 over 1 times 2 over 5, we get 20 over 5, which again is 4. So 10 divided by 2.5 and 10 times 2 over 5 end up being the same thing. All of which to say, when we divide by fractions, we multiply by reciprocals. They're the same process, right? So when I go back over here and I see these two rational expressions, I should be thinking the same thing. Of course, this first quantity, whatever it is, whether it's 10 or 5 over 7, or this rational expression, 5x squared over 7, of course I want to keep that the same, but I'm going to turn that division by 10x cubed over 21 into multiplication by the reciprocal. And once I do that, I just cancel the way we normally cancel from the last lesson. I might notice 7 and 21 share a common factor of 7, and I'm going to divide that factor out. I'm going to cancel it out. 5 and 10 share a common factor of 5, and I'm going to divide that 5 out. X squared would be 2x's over x cubed. There would be one of them left over where the larger power is, which here is the denominator. And then, of course, I just want to make sure, I've said several times, don't lose track of what sticks around. We've got a 1, we've got a 3, we've got a 1, a 2, and an x in our denominator. And so that's why we can say pretty easily here, oh, so this is simply 3 over 2x. Now, I did mention there was a difference between simply dividing by fractions and dividing by what we call rational expressions. And that difference has to do with, once again, our excluded values. I cannot allow values that would cause a denominator to ever be equal to 0. So as I look at the original part, you might say, well, what's the big deal? 7 can't be 0. It's not 7x, it's just 7. 21 can't be 0. But there's an additional thing I have to watch out for when I'm dividing by these rational expressions, because again, I'm not allowed to divide by 0 at all. So in this case, I'm not just looking at denominators, I also have to look at anything in that second expression that would cause the whole thing to be equal to 0. So that means that I also cannot let x equal 0 in this case, because if I did, it would cause that second fraction, the whole thing, to be equal to 0, and I would still be dividing by 0, and that is not okay. So that is the one additional thing we have to do here. We identify, yes, this expression is the same as 3 over 2x, so long as x is not 0. Unsurprisingly, we can do this with binomials or trinomials or any other kind of polynomial. It doesn't just have to be monomials. So I'm looking at example 1b now, which has the rational expression n plus 1 over n plus 3 divided by 2n plus 2 over n plus 4. At this point, hopefully you kind of understand, yes, of course we're going to flip this around times n plus 4 over 2n plus 2, and that original expression, nothing changes there. And you should also be used to, from the previous lesson, multiplying rational expressions. You should also be used to immediately factoring any expression you notice that is factorable. So 2n plus 2, you should see, oh, that's the same thing as 2 times the quantity, n plus 1. That is the distributive property in reverse. We have to be able to pull that 2 out of both of those terms. From here, I'm going to quickly identify my excluded values. I actually remembered to do that this time. Of course, looking at this denominator, n cannot be negative 3 because it would cause that denominator to be 0. Of course, n cannot be negative 1. But also, remember, our original denominator back up here was actually n plus 4. So n also cannot be negative 4. What that gives us after we have identified all those excluded values, so let's make sure to have those highlighted, and we have canceled whatever we can cancel, I can see here that is simply an n plus 1 with an n plus 1. I get my answer, which is going to be an n plus 4 in my numerator and an n plus 3 times 2 in my denominator. Now I can, if need be, multiply that out in the denominator and call that 2n plus 6. I could do my distribution, but there's no special reason that you have to. The factored form is fine. Take a moment and work out, check your progress. 1a, 1b, 1c, and 1d. Okay, so coming back in here, that took a few minutes. Check your progress 1A, we've got 6x squared y, x cannot be 0, y cannot be 0. Check your progress 1B, we've got 243d to the fourth e over 22, provided that c, d, and e, none of them are 0. Check your progress 1C, I simplified down to b plus 1 over 3b plus 2 times 3. Of course, you could have multiplied that out. Not that there's any reason you have to. It would have been b plus 1 over 9b plus 6, provided that b is neither -4, -1, nor -2/3, because of the various factors that would have ever caused a denominator to be 0, or something that you were dividing by as a whole to be 0. Finally, check your progress 1D. I've got b minus 2 over 3 times the quantity 2b plus 3. Again, you would not need to do this, but if you want to multiply that out, that's the same thing as 6b plus 9, provided b is not -5 or -3 over 2. For the same reasons we've already talked about. Let's go ahead and jump into example 2. Not super different from what we've already done. We have m squared plus 3m plus 2 over 4 divided by m plus 2 over m plus 1. And I notice a few different things here. First of all, this denominator 4 cannot be made to be 0, but m plus 1 could definitely be 0 at -1, so that's no good. And again, this whole thing could be made 0 if m were -2, so we can't let that happen. So we end up with those two excluded values. Otherwise, let's go ahead and factor this. Two numbers that multiply up to 2 but add up to 3 are 2 and 1. So that's how that factors. The 4 stays a 4. Our division we want to turn into multiplication, and of course we want to flip that upside down. And when we do that, we can see, the m plus 2's cancel, and so I end up with m plus 1 times m plus 1 over 4, which we could also write, if we wanted to, as m plus 1 squared over 4, or we could even expand it out with box method and write it as m squared plus 2m plus 1 over 4. Of course, the one thing we definitely will not do here is say that this is m squared plus 1 over 4, because we don't want God to kill a puppy. Okay. Take a moment and work out check your progress 2A and 2B. All right, that is my work for Check Your Progress 2A and 2B. A little bit strange on Check Your Progress 2A. I'm not sure if this is a typo that maybe was only in my book. If this was P plus 9, obviously this would be a little different, but in my book it's a P plus Q. So a couple things to say about that. First of all, obviously it's not going to factor out later, so you can still see the P plus Q in my answer here. But then it also gives us kind of a strange excluded value. So remember where these are coming from is we're saying, well, it can't be the case that that denominator 5p is 0. But we can almost treat it like an equation at that point, and that's where we get p cannot be 0. And up here, same thing. What we're really saying is p minus 2 cannot be 0. But again, if you add 2 on both sides, that's where we're getting, oh, so p cannot be positive 2. So we can do the same thing here. We can say, well, p plus q cannot be 0. And if we subtract the q on both sides, that's where we get the kind of strange excluded value, p cannot equal negative q. So basically p and q can't be additive inverses. Otherwise we would end up dividing by 0 again. From there though, the p minus 2's after you factor are the only part that cancel, and so there's your answer. P plus 2 times the quantity p plus q divided by the 5p. And again, you can see we turned our division into multiplication and flipped that second rational expression upside down. Over here, similar kind of situation, 12 cannot be made into 0 at all, so no excluded value there. Q plus 1 could be made into 0 at negative 1, so negative 1 is an excluded value. But then q squared plus 4 is interesting. Q squared plus 4 cannot equal 0, but there is no real value of q that would cause that to happen. When you square a number, the least value you can ever get is 0, and then from there it only goes up. Negatives squared make positives, just like positives squared make positives. So if you're adding 4 to something that at minimum is 0, the least this can ever be is 4. And so again, presuming that q is at some real number, there is no way that q squared plus 4 can be made to equal 0. So there's no excluded value to worry about there. The other way to think about why q squared plus 4 can't be 0 has to do with what you might try next, which is factoring. Some of you might have thought, wait a second, isn't that just q plus 2 squared? But again, if you take that to the box method and you put q plus 2, q plus 2, and you multiply that out, you're going to see, oh, wait a second, it had that middle term 4q. And of course we don't have a middle term up here. It's just q squared plus 4. So no, we can't end up factoring that as q plus 2 squared. It also won't factor as q minus 2 squared. Of course it also won't factor as the difference of squares, q plus 2, q minus 2, because the plus 2 and the minus 2, when you multiply them together, should be negative 4, not positive 4. All of which to say that does not factor at all. When you flip it around, it's not going to cancel with anything. The q plus 1's from the factoring do cancel though, and that's how we end up with q plus 2 times q squared plus 4 divided by 12. All right, one last example. Let's take a look at example 3. We have some dimensional analysis. In April 2001, NASA launched the Mars Odyssey spacecraft. It took 200 days for the spacecraft to travel 466 million miles from Earth to Mars. What was the average speed of the spacecraft in miles per hour? Round to the nearest mile per hour. So I actually don't like the way they approached this. Of course, it is true that you could use rate times time equals distance and plug in, but the whole point of dimensional analysis is that we shouldn't have to think about that stuff. So we're given a couple different things. We're given 466 million miles in 200 days, but what we want to do is convert this into a speed in miles per hour. So the only thing we should have to do is use a unit converter to turn days into hours, because miles and miles are already the same, right? So this should actually be a really simple dimensional analysis problem. Multiply by your unit converter. Since days is in the denominator here, we want it in the numerator. Since hours is what we're trying to turn it into, that goes down here. And then we just need to write what the relationship is. 1 day corresponds to 24 hours. And so what we're going to end up doing is canceling our days with days. We can also cancel a couple zeros here. If we needed to do a little bit more, 2 goes into 466. 1, 2, 3, 4 zeros remaining there after we do our cancellation. And so really this turns into a calculator problem. What is 2330 with another 3 zeros divided by 24? 2, 3, 3, 1, 2, 3, 4 divided by 24. And I'm getting 97,083 and change. So this is the same thing as roughly 97,083 miles per hour. So pretty fast. Take a moment and work out check your progress number 3. Okay, so Wolfram Alpha told me it was 202 days from July 7th, 2003 to January 25th, 2004. So presuming everything else is the same, we get our times 1 day to 24 hours gives us an answer in miles per hour of 96,122 and change. 96,122 miles per hour. Lesson 11-4, dividing rational expressions. The key is keep, switch, flip. You're going to multiply by reciprocals because that's how we divide by fractions or fraction-like objects. Dimensional analysis still works here. If you want to turn it into a division problem, do so, but if not, don't worry about it. Make sure to comment with any questions that you have, and I will see you all later.